Have you ever stopped and thought about this? A fully loaded passenger jet weighing 250 tons is descending through a thick cloud layer. Outside the windows, there is nothing. No horizon, no ground, no runway. Visibility is less than 50 meters. And yet the aircraft touches down precisely on the centerline, within the first 300 meters of the runway, at exactly the right speed. The pilot never saw the runway until the last 2 seconds. So how does that happen? And here's where the most common assumption needs to be corrected right away. Most people think the pilot is always flying the aircraft manually during landing, but in the most demanding conditions, the ones where visibility is near zero, the pilot is not flying at all. The aircraft is. And understanding why that's necessary tells you everything about how the system actually works. Let's start with the problem. The human eye is remarkable at many things, but landing a 250-ton aircraft in zero visibility is not one of them. To land safely, a pilot needs precise information about 3 things simultaneously: lateral position relative to the runway centerline, vertical position on the correct descent path, and distance from the threshold. In clear conditions, the eyes provide all of this instantly. In fog or low cloud, they provide none of it, and the aircraft doesn't slow down just because the weather is bad. It's still descending at roughly 700 feet per minute, covering 70 meters every second. That's the problem. Now let's talk about the solution. The Instrument Landing System, the ILS, has been guiding aircraft onto runways since the 1940s. It sounds old, but the core principle behind it is still the foundation of every precision approach flown today. The ILS consists of 2 separate radio transmitters located at the runway. The first is the localizer. It transmits a directional signal along the extended centerline of the runway, in a narrow horizontal beam. When the aircraft is perfectly aligned with the runway, it sits in the center of that beam. Drift left, and the signal shifts one way. Drift right, and it shifts the other. The cockpit instruments show the deviation in real time, and the pilot, or the autopilot, corrects immediately. The second transmitter is the glideslope. It works in exactly the same way, but vertically. It projects a beam at a fixed angle, typically 3 degrees, from the runway threshold upward into the approach path. Too high, and the signal shifts. Too low, and it shifts the other way. Together, the localizer and glideslope define a precise 3-dimensional corridor in the sky. Fly down the center of that corridor, and you will arrive at the correct point on the runway, at the correct angle, every time. But here's the important part. The ILS tells you where you are. It doesn't fly the aircraft for you. That's where the autopilot comes in. And in low visibility conditions, the autopilot isn't just a convenience. It's a requirement. Here's why. Think about what a landing actually involves in the final 60 seconds. The aircraft is descending, decelerating, configuring its flaps, managing its energy, and staying precisely on a path that is only a few meters wide. Any crosswind is pushing it sideways. Any gust changes the lift. Any speed variation changes the descent rate. A human pilot can manage all of this in good visibility, because the visual feedback is immediate and continuous. But remove that visual feedback and replace it with instruments that require interpretation, and the reaction time increases. In conditions where the aircraft is 30 meters from the ground and still inside cloud, there is simply no time for interpretation. The corrections need to happen faster than a human can make them. That's the category system, and it's more structured than most people realize. A category I approach, CATI, requires a minimum decision height of 200 feet and a runway visual range of at least 550 meters. At that point, the pilot must see the runway environment to continue. If they don't, they go around. This is the most common type of precision approach, and most commercial pilots fly them every day. Category 2 raises the bar significantly. Decision height drops to 100 feet. Runway visual range down to 300 meters. At this level, the autopilot must be coupled to the ILS. and the aircraft and its systems must meet specific certification requirements. Category 3 is where it gets extraordinary. Cat 3A allows a decision height as low as 50 feet and visual range as low as 200 meters. Cat 3B pushes that further, decision height below 50 feet, visual range as low as 75 meters. And Cat 3C, the theoretical maximum, specifies 0 decision height and 0 visual range. The aircraft lands without the pilot ever seeing the runway at all. To perform a Cat 3 approach, the aircraft must be equipped with a fully certified autoland system. And an autoland system is not simply an autopilot that follows the ILS. It is a redundant, self-monitoring, fault-tolerant control system that is a completely different engineering proposition. Here's how it works. The autoland system uses multiple independent computers running simultaneously and comparing their outputs constantly. On a typical modern airliner, there are 3 or more flight control computers involved in the autoland sequence. They monitor each other. If one computer produces an output that differs from the others beyond a defined threshold, it is voted out of the system, and the remaining computers continue. This is called dissimilar redundancy. The logic is simple. No single component failure should be able to cause the aircraft to deviate from the correct flight path during the most critical phase of flight. As the aircraft descends through the final approach, the autoland system is simultaneously managing the throttles, the control surfaces, and the flight path based on continuous ILS inputs. At 50 feet above the runway, a key transition happens. The system switches from the ILS glideslope signal to the radio altimeter. The ILS glideslope is accurate at distance, but its precision degrades very close to the ground because of antenna geometry. The radio altimeter, which measures the direct distance to the surface below the aircraft, takes over for the final few feet. At around 30 feet, the system initiates the flare. This is the gentle nose-up rotation that reduces the aircraft's sink rate just before touchdown. The flare maneuver must be timed precisely. Too early, and the aircraft floats down the runway. Too late, and it lands hard. In manual landings, pilots develop this feel over thousands of hours. In autoland, it is computed from radio altimeter rate of descent data and executed automatically. Touchdown happens, and the autoland system doesn't stop working. It transfers immediately to rollout control, keeping the aircraft tracking the runway centerline using the localizer signal and the nose wheel steering. The auto brake system activates. The spoilers deploy. The thrust reversers engage. All of this happens in a coordinated sequence without any input from the pilot. The pilot's role in a full Cat 3 autoland is to monitor the system, be ready to take over if something fails, and apply maximum braking manually if the auto brake doesn't engage correctly. But this system has real limits, and they're important to understand. The ILS ground equipment at the runway must be certified to the same category as the approach being flown. A Cat 3 approach requires Cat 3 ground equipment, which is more expensive to install and maintain, and requires a specific obstacle-free zone around the antenna that not all airports can provide. This is why Cat 3 capability is not universal. Many airports around the world are Cat 1 only, which means that when visibility drops below Cat 1 minimums, operations stop regardless of what the aircraft can do. Crosswind is another hard limit. Autoland systems have maximum certified crosswind components, typically around 15 to 20 knots depending on aircraft type. Above that, the system cannot guarantee centerline tracking to the required accuracy, and the approach must be flown manually, or the landing must be diverted. And the aircraft itself must be specifically certified for the category it's flying. Not all aircraft with autopilots are certified for autoland. The certification process requires extensive flight testing to demonstrate that the system meets the required accuracy and failure tolerance standards across a full range of conditions. So the next time you land in fog and the touchdown feels unusually smooth and precise, that's not a coincidence. The aircraft flew itself onto the runway with an accuracy that no human could consistently replicate in those conditions. It tracked a radio beam to within a few meters, flared at the exact right moment, and rolled out on the centerline, all without the pilot seeing the ground until it was already there. That's not autopilot in the way most people imagine it. That's a redundant, fault-tolerant, self-monitoring control system, executing one of the most geometrically demanding maneuvers in aviation. And it does it in conditions that would make a manual landing impossible. To me, that's the real engineering story behind every foggy landing you've ever experienced without knowing it. I've already covered how the braking system takes over after that. That's a different video. But there's one more layer to this that most people never think about. What happens when the ILS itself fails during the approach? This is not a theoretical question. ILS ground equipment can experience interference from other aircraft taxiing near the antenna, from heavy vehicles crossing the signal path, or from atmospheric conditions that distort the beam. In a cat-eye environment with a human pilot flying visually, a brief ILS anomaly is manageable. The pilot sees the runway and corrects. In a Cat 3 environment with zero visibility, an ILS anomaly during the final 200 feet is a different situation entirely. This is why modern aircraft equipped for Cat 3 operations carry a secondary navigation source that monitors the approach independently. GPS-based systems can cross-check the ILS position data and flag discrepancies before they become critical. The autoland system itself monitors ILS signal quality continuously and will alert the crew or initiate a go-around automatically if signal integrity drops below the required threshold. Again, redundancy. Not because the system fails often, but because in the conditions where it matters most, a single point of failure is not acceptable. And this is also why Cat 3 approaches require specific crew training and certification. Pilots who fly Cat 3 approaches regularly practice not just the normal procedure, but the failure cases. An auto-land failure at 100 feet, an ILS fault during rollout, a go-around initiated by the system at minimums. The pilot's job in these conditions is less about flying and more about systems management and decision-making. It requires a different kind of skill than the hand flying that most people associate with being a pilot. The result of all of this, the ground infrastructure, the aircraft certification, the crew training, the redundant computers, the radio altimeter handoff, the automatic flare, is a system that allows commercial aviation to operate in conditions that would have grounded every aircraft ever built just 60 years ago. Visibility that would stop a car on a motorway is now a routine operating condition for a properly equipped aircraft and crew. That's the engineering behind the foggy landing you thought the pilot just handled. They were managing it. The aircraft was flying it.